There we are. Yeah, welcome to the I guess the video about how the ocean is changing. So we've had some introductory videos about how the ocean works, how climate change, kind of the fundamental mechanisms behind that, and we've also covered some ocean chemistry changes, looking at ocean acidification. And this video will look at the ocean heat content and how that is changing. So just make this work. Yep, so the ocean heat, so we're getting warmer, variety of reasons behind that, mostly CO2 in the atmosphere, warming up the atmosphere, and then the atmosphere is then kind of warming up the ocean. So as we saw in a previous video, most of the heat kind of content, or the increase in heat content of the Earth system has actually gone into the ocean. It's why the surface temperature is so kind of variable, really, is that the bulk of the heat is going into the ocean, and the variability we see with the Earth's surface temperature is really due to exchanges of heat between the atmosphere and the ocean. So if we just take a little bit of a closer look now at about where the heat is going into the ocean. So we're going to take this graph here of how the ocean heat content has been changing through time. And over here on the left, we're just looking in a little bit more detail about where that's gone into the ocean. So the different shades of blue here are different, basically, layers within the ocean. So the top of the ocean, the top 300 meters, is the light blue, and we can see that that's kind of one of the largest components. And then as we progressively go down into the deeper ocean, so the darkest blue, one of the 2,000 meters bottom. Okay, so kind of ocean is, I guess that's almost half of the ocean, only has a small amount of the heat content in it. So what we can see from this is that the ocean hasn't warmed up uniformly throughout the whole ocean. It's predominantly warmed in the surface layer. Looking over onto the right-hand side, we can see that actually it's not kind of uniformly distributed around the globe. So in that, I guess this is now the top 700 meters, so basically the top two layers of the plot on the left. We can actually see that there are spatial patterns. Some regions of the ocean have kind of warmed up more, and some warmed up less. So that'll have an impact on kind of those kind of regional, on a regional scale, particularly for coral reefs in a warm zone, are obviously going to experience more warming, or have experienced more warming into the future. So let's have a look at, I guess, one of the most, visible impacts of this increase in heat content. We've already mentioned this before. This is looking at the sea level rise. So we're going to have a look at sea level rise first, just quickly, and then we're going to have a look at some extreme events in terms of the ocean heat content, which are particularly relevant to coral reefs. So just quickly having a look at sea level rise. So this is a graph of measured of satellite altimetry, a bunch of different kind of processings of effectively the same data. And so we've got quite good agreement here. We kind of pretty much know reasonably well that we're looking at maybe a few centimeters of sea level rise over the last kind of 20, I guess this is almost 40 years, 30 years. Use my math brain here. Anyway, so sea levels a few millimeters a year has been rising, and this is largely due to the thermal expansion of seawater. But again, just like with the heat input, this pattern of sea level rise is not kind of uniform over the whole globe. It's determined by the spatial distribution of heat energy. Also, freshwater fluxes can have an impact, because different salinities of water are different densities, so they affect the sea surface height in some regards. But also, an additional factor which might not be so obvious is that the sea level is not level. So it has dynamic topography on it. So if you were to actually kind of like freeze the ocean and make a completely frictionless surface, and you would dump a bunch of marbles on it, they would roll around, because the sea surface is not flat, because ocean currents and the action of winds cause water to be variously piled up in different parts of the globe. So this leads to these three effects of differential heating, ocean circulation, and freshwater fluxes, lead to quite a I guess a heterogeneous spatial distribution of sea level rise over the last I guess couple of decades. And this is important because this can have quite strong impacts on kind of local coral reefs. If a particular region has experienced more rapid sea level rise than elsewhere, the impacts may be different. So, I mean, if you think about maybe a few centimeters of sea level rise, we're looking at maybe projecting forwards to the end of the century. We might even get towards a meter of sea level rise. Does this really matter for coral reefs? If you're a coral and you suddenly see a little bit more water sitting above you, that's not going to have an immediately obvious impact. Coral would be pretty happy living in 1 meter of water depth versus 2 meters of water depth. It would be maybe a little bit less light, but on the grand scheme of things, the depth of water, if it's increasing, is not such a problem. Obviously, if sea level is decreasing, that's a very big problem for coral reefs because they don't like living in the atmosphere not much. But actually, on a longer kind of time scale, decades to maybe hundreds of years, the ability of coral reefs to keep up with sea level rise is not infinite. So this is a study came out a couple of years ago, looking at measuring or estimating the ability of coral reefs to accumulate vertically through coral growth. So over on the left-hand side, we've basically got estimates of the amount of calcium carbonate that different coral reefs can produce per year. And you can see that coral reefs generally accumulate calcium carbonate because they grow these skeletons. And over on the right hand side, what we're seeing here is for a bunch of sites in the Atlantic. The paper actually covers the Indian Ocean as well, but just to simplify things in the Atlantic, what's happened is they've converted these kind of mass accumulation rates of how much carbonate a coral can produce into an ability for a coral reef to accumulate matter vertically. So basically growing up into the water that's overlying the corals. And they've compared that to a bunch of different sea level rise scenarios. So at the top, this is basically our current rate of sea level rise measured from satellites. And then the bottom two are some projections. And what they've done is they've basically taken the accumulation rate estimated from field measurements and then taken away the sea level rise. So you can see in the top plot, most of the data hover just around zero, maybe a little bit below. So that shows that the coral reef growth can just about keep up with our current rates of sea level rise. But as we move forwards towards, I guess, the end of the century, and looking at some accelerated sea level rise rates through further warming and potentially significant melting of polar ice sheets, the amount of accumulation of the corals can't keep up with the sea level rise. So under all of these scenarios, the corals will effectively drown. They'll basically be moving. The surface of the ocean will be moving up away from them. And this has kind of important implications for the long-term viability of coral reef habitats. So there's more in this paper, which will be posted on the Learn site, which you can kind of read through. So sea level rise, not an immediate problem for a variety of most coral reefs, but in the medium to long-term future, it's very much a problem. Okay, so now we're going to be looking at some of the heat content of the ocean, rather than kind of just the expansion of the ocean as a result of that heat content. And really, we're going to be looking at not so much the average temperature, so this long-term warming, which we've already covered, but looking at some of the variability on that warming and see how that has been changing and is likely to change into the future. So I guess in the atmosphere, we're quite used to thinking about weather and kind of the conditions that we experience kind of year on year. So you'll be quite familiar that we don't usually experience kind of the average annual temperature every day of the year. Sometimes you might have a few weeks of warm weather, cold weather. Maybe one year might be have a particular kind of strong heat wave in the summer, or it might be a very cold summer. So we get quite a lot of variability within the year and between years in the conditions that we experience. And this is just an example from earlier in 2020. So Siberia experienced quite an intense heat wave for a number of months, where the temperature was significantly warmer than it would usually be for that time of the year. And I guess the impacts of that were that the forests in Siberia were a lot drier than usual at the beginning of the year. So in the middle of the year, that led to large forest fires, more melting of permafrost and damage to infrastructure. So it has quite important societal impacts, this weather variability in the atmosphere. Now, just like, I guess, the atmosphere, the ocean has variability too, and we'll be looking at that shortly. So just to give a little bit more context about how these extreme warm events might change in the future. So here are some data from central England. So I think these are data from about 1750 to present. And what's plotted up here are it's a histogram of the warmest day in each year. Okay, so you can see that in some years the warmest day was actually quite cold. It really never got above 20 degrees Celsius at any time during the year, whereas in some years it's got considerably warmer. So we've had some days where the warmest temperature at this particular location was over 30. But on average, the warmest day in each year is going to be around 22, 23 degrees Celsius. I just point out that the odd look of this data. So I guess all of these peaks and troughs here, kind of alternating. That's due to a change in the accuracy of the data. So I guess in the early part of the record, data were only recorded to a half degree, whereas the latter portion of the record they're reported to a quarter of a degree. So we get more fine resolution in the later part of the record. But anyway, it's all bundled in here. So if we have a look at the extreme events, okay, we see that the actual likelihood of any one year being maybe above 30 degrees Celsius, or having a day above 30 degrees Celsius, is actually quite small. So it's just these part of the distribution here. So maybe if you look at the area of this plot, this part down here, compared to the area of the whole distribution, which looks like this, that's poorly drawn, obviously, not like that. We're looking at there's maybe a less than 5% chance of having an extremely warm day in any one year. But what would happen if we were to change the average temperature? So if we look at taking a similar distribution and just shifting the mean here, we shift the mean, then if the whole distribution moves, what was if we did have a low, oh no, we've lost our thing, lost our pointer options pen. Here we go. So what was a low probability of exceeding kind of this temperature, if we shift the mean just a small amount, because of the sloped nature of this distribution here, as we move this edge of the distribution towards warmer temperatures, the actual likelihood of exceeding that extreme warm kind of threshold temperature is drastically increased. So by shifting the mean temperature a little bit, we greatly increase the likelihood of exceeding a particular temperature in any one day. We can also change the likelihood of exceeding a temperature by just changing the shape of the distribution. So if we make our weather more unpredictable, so if we start to smooth out the distribution, then that can also lead to an increase in the likelihood, or the basically the area under this extreme kind of threshold value here. Now, it's unclear whether in the ocean we're actually changing the variance, so we're spreading out the distribution, but we definitely are increasing the mean temperature. So this is definitely happening in terms of the overall average of the ocean. But this could also be occurring. But either way, we are increasing the likelihood of experiencing very, very warm weather in the ocean. So what do I mean by weather in the ocean? So here's a map a couple of years ago now of the surface temperature of the ocean, and you can see that the equatorial regions are a lot warmer than the polar regions. That's kind of quite obvious because they're receiving more incoming solar radiation per square meter. But actually, it's a little bit more informative to not look at the absolute temperature, but look at the temperature anomalies. So these are each kind of grid square, each kind of pixel in this image. It's the temperature on the 14th of August 2018, basically minus the kind of the average temperature for the 14th of August for previous years. Okay, so we can see that various parts of the ocean here. We can see that where's my little pointer? We can see that this region of the Pacific is cooler by a few degrees than it would normally be, as is kind of Arabian Sea over here. But there are other regions which are warmer. So off Korea, Japan here, off Baja California, which is the North Atlantic, are particularly warmer than average. So we can see that there are, the bits of the ocean can be warmer or cooler, just like the atmosphere can. So another way of looking at kind of trying to quantify these extreme events, rather than looking at maybe just the temperature, we can look at trying to quantify or parameterize something that will give us an indication of a heat wave in the ocean, or an excessively long period of time where there is prolonged increased temperatures. So what we can use for that is this parameter called degree heating weeks. So what this is that for each kind of pixel in the map, we're looking at how many kind of degrees warmer times the number of weeks it has been that warmer in that pixel compared to kind of the long-term average. So we can see that these purple regions, they've either been kind of 1 or 2 degrees warmer for maybe 1 week, or they might be 1 degrees warmer for 2 weeks. And these red regions up here, they've been 8 degrees, so off Korea and North Atlantic, they might be 8 degrees C warmer for 1 week, or only a little bit warmer, 1 degree C for 8 weeks, or 2 degrees C warmer for 4 weeks. So this parameter gives us some kind of estimate of a combination of the duration of extreme warmth and the magnitude of extreme warmth. Now, that's not a perfect kind of proxy for marine heat waves, but it does provide a useful metric for us to assess the relative impacts for coral bleaching. So corals don't like it when it gets particularly warm, and importantly that warmth persists for a long time. If it returns to normal conditions after a while, the impact on coral reefs is less, and we'll come on to that in other sessions on coral bleaching. So this was the 14th of August 2018, and this was another time in the past, I guess now 4 years ago, and we can see that there are extensive regions of the southern hemisphere which are undergoing quite intense marine heat waves. So we've got the equatorial Pacific here, so that's much warmer and has been warmer for a long time than it would normally be. You've got regions over kind of New Caledonia here and around kind of the Indian Ocean, so the British Indian Ocean territory, not our finest hour over here, experiencing particularly warm um, uh, conditions. So this is a entirely natural phenomenon. It's just like the weather in the atmosphere. The ocean temperatures do occasionally get warm and then cool down again as heat is transferred around from different parts of the ocean and between the ocean and the atmosphere. But what I have to do now is have a look at how this has actually been changing. Oh, I should just we should just have a look at this. Here's a little fun video. I need a pointer to make it work though. I get pointer. Pointer options. I just want a pointer. Okay. Oh well. Ignore this. Pointer options. Go. Here's a nice video of coral reef, I think in the Maldives. And this is one of the these impacts of extreme warm events. So here you can see some corals. I think these are aquapora corals. Anyway, and some fish, lovely fish. And you can see that the majority of these corals are bleached. They've lost their symbiotic zooxanthellae. Oh, there's some over here that are not bleached. Lovely coloured ones over here. So not all of the corals have been affected, but this extreme warmth has damaged the coral reef. They're not yet dead, so if the heat wave ends, then they could recover, they could recapture some zooxanthellae from the water and regain their ability to photosynthesize. Oh no, I will try and get myself my pointer back. Go, pen. Right. So how are these extreme heat waves changing? So there's a lot of stuff going on in this figure. So just talk you through it. So at the bottom, J and K. So J is the sea surface temperature. So this is not terribly informative. It's telling us that it's kind of warmer in the equator, cooler at the poles. And what these plots are all doing is they're basically looking at the difference in the average conditions in the 2000s and early 2010s and compared to the 80s and 90s. So we can see down at the bottom in K, this is the sea surface temperature in the 2000s and early 2010s, minus that in the 80s and 90s. And we can see that over large parts of the Atlantic and particularly the Western Pacific and Indian Oceans, Atlantic Oceans, these are 1 or 2 degrees warmer than they were in the previous decades. And that is reflected over in L over here. So this is L. We can see that shown as basically the globally average sea surface temperature trend has been increasing over time. Okay. So that's the temperature. So we've had a gradual increase in temperature through time, but how has this affected our extreme events? So we've got 3 kind of ways or metrics of these marine heat waves. We've got the frequency, we've got the intensity, and we've got the duration. So we can see that over the whole ocean, the typical frequency of these extreme warm events is somewhere between kind of 2 and 3. So we might expect in any one year we might get 2 or 3 of these heat waves. But if we look at how that's changed over the last few decades, we can see that frequency has increased in the areas in the ocean which have got warmer. So the Atlantic and the Pacific and Indian Oceans. These regions of the ocean have not only got warmer, but they are experiencing more frequent heat waves. We can also look at how intense those heat waves are. So we can see that actually there's a little bit of more of a spatial pattern to those. They tend to be more intense along the equator, along the upwelling regions, which are associated with the El Nino Southern Oscillation. We'll come on to that in a future slide. And in the kind of the Gulf Stream and the Kurashiro current. So these are ocean circulation phenomena that are leading to spatial patterns in these heat waves. So there's a close link between ocean circulation and heat waves as well. And we can actually see that the intensity over most of the ocean has actually gone up a little bit. It's got more in the North Atlantic and the North Pacific, but the intensity not really changing a huge amount. So they may be getting maybe half a degree warmer, these extreme events on average, but in some regions like the Equatorial Pacific, they're actually getting less intense. And then lastly, we can look at the durations, which is just as important as the intensity for the impacts of these heat waves on coral reef communities. And we can see that in some regions around, I guess, the Galapagos Islands, in the Equatorial Pacific, the duration of these extreme events are actually getting shorter. But actually, over most of the Pacific and Indian Oceans, Atlantic, they are getting a little bit longer. Maybe they're lasting a week or so longer, 5 to 10 days, maybe 2 weeks in some cases in the Central Pacific. So on a global kind of summary, the ocean's getting warmer. That's this one down here. We're having more frequent ocean heat waves. Those heat waves are a little bit more intense, but in some places that's not true. And also they're getting longer in duration, so that we're getting more extended periods of extreme warmth. That's this one here. Again, and then we can look over on the right-hand side at the time series of these changes. Okay, so we can see that these changes shown in the maps are also shown in the frequency is increasing, intensity also increasing on average, the duration increasing a little bit, less of a clear signal except in the last kind of few years. Now, it's worth just having a little bit of a closer look at these things over on the right-hand side in terms of the time series. And that there are two sets of data plotted here. They've got the global average in black, and then the red are data which exclude the variability associated with the El Nino Southern Oscillation. So that means that the black is actually showing us some extra variability due to this El Nino Southern Oscillation. And if we look at some of these years with more extreme events, so that's, I guess, these data here, these peaks. So these are in, I guess, 1997, 98, we had, and 2016, we had particularly long heat waves that are associated with El Nino periods. So the red vertical stripes, these ones here, are El Nino years, and we can see that there's we tend to have more longer. So we have, I guess, we have more. We have more intense, and we have longer. These ones here, extreme events during these El Nino periods. So let's just have a quick recap of what the El Nino kind of southern oscillation is. So this is a phenomenon that occurs in the ocean and also in the atmosphere, so that the system is kind of coupled together because the atmosphere is heated by the ocean and the ocean is heated by the atmosphere, and the winds blow around the surface of the ocean, and basically the strength and location of the winds are determined by the heat kind of distribution patterns within the ocean, which causes atmospheric convection. So the two are completely tightly coupled together. And what we can see if we actually have a look at the sea surface temperature maps at the top here are in a La Nina kind of situation. most of, or the warm water in the Pacific is concentrated over towards the western side. And what that effectively does is that causes, in this region here, we get a lot of warm water over in the west, and that sets up very strong atmospheric convection over here. So we get kind of this, I'm going to try and draw a big cloud over here. This is a cumulonimbus cloud. Imagine that's a cumulonimbus cloud over here, because we get lots and lots of rising air. Okay, whereas over in the eastern Pacific, the water is relatively cooler, so this leads to kind of like descending atmospheric circulation, which leads to winds that tend to blow this way and reinforce this piling up of warm water over on the west. Now, in an El Nino year, that atmospheric circulation breaks down, and the warm water is more evenly distributed over the whole of the Pacific. So if we look at the anomaly maps of that, we can see that the El Nino, this redistribution of warm water over towards the east leads to anomalously warm conditions over in the eastern Pacific, whereas in a La Nina year, we have basically more evenly distributed water or heat across the Pacific. Now this has, again, this changing spatial distribution of heat will have basically an effect on how warm the water is, which will then inform how kind of extreme the heat waves are in either of these regions. Just to look at how this, I guess I should have probably flipped to this slide rather than draw it myself. So we can see that during La Nina year, we have warm water over in the west. That leads to rising air, which leads to an atmospheric circulation setup that looks like this, which pushes the warm water over here, which leads to us having rising air over the west. We've got low atmospheric pressure here. We've got, in this region here, we've got high pressure over here. So there's a coupling between atmospheric pressure and the distribution of ocean heat. And this has wide-ranging implications for weather. So it makes, if you have lots of warm air over the western Pacific, that leads to having lots and lots of thunderstorms over that region, makes it very, very wet. And conversely, when the center of atmospheric convection moves to the east, moves this way, that leads to there being lots of rain here, and no rain here, which has big impacts for kind of the communities that live there in terms of drought and fire and other hazards like that, but will also impact kind of the reefs in terms of changing runoff from the land, in terms of adding sediment and other nutrients being flushed off into the reef systems, but will also be changing the heat distribution in the ocean, which will affect these extreme warm events. So one question we could maybe pose is how will these changes in the basically the way that the Pacific Ocean works, how will they change in the future? So should point out that we can basically characterize what state the Pacific is. Is it one of these El Nino situations where the heat is more evenly distributed over the Pacific, or is it a La Nina where it's moved all over to the west? In a number of different ways. So we could one way is we could maybe if we make two weather stations, one here and one over here, and measure the atmospheric pressure difference between those two, that would tell us about the state of atmospheric circulation. And the difference in pressure between these two sites gives an index of what state the atmosphere-ocean system is. Another way is to basically just take a box of the ocean, one of these boxes, and work out what the average temperature is in that box. And when these boxes over on the eastern side, they're warmer than usual, then we're in an El Nino state. Whereas if they're cooler than usual, we're in a La Nina state. And that's what's plotted down here at the bottom. And what we can see here is that there's this quasi-periodic switch between being in El Nino, and then it switches to a La Nina state. El Nino, La Nina, Nino, La Nina, and it switches between these on a cycle approximately kind of 3 to 5 years. Now, it was important for us to know how this will change in the future, because in these El Nino years, this is when we tend to have more extreme kind of ocean heat waves. So these are years which will lead to more coral bleaching and bad times for coral reefs. So we kind of want to know whether the uh, um, the Earth's or the El Nino system will change from being kind of predominantly more El Nino-like or La Nina-like, or whether it will be more extreme El Ninos or less extreme El Ninos. Or we might want to know whether the frequency might change. So the only way that we can look into the future is by using climate models, and we can basically run those climate models under current atmospheric conditions, current greenhouse gas conditions, and then we can run them again with kind of future climate change scenarios. And within those climate models, we can see how the El Nino system behaves. And that's what's shown here on the right-hand side for two basically different metrics. The Nino 3, which is this one, which is basically average temperature in this box, and the Nino 4, which is the average temperature in this box. And what's plotted here is the variability. Okay, so we're looking at how the variability is different under normal conditions and under climate change scenarios. So we can see that these data here, or these model runs, have shown that under a control conditions, we were getting a variance, normalized variance of about 0.8, and now this model here, oh no, we didn't want to do that. This model here is now at a variance of 1.2. So these data that fall above this one-to-one line, these are models which show that we're getting more variability in the El Nino system. So we're getting more extreme El Ninos, or extreme La Ninas. But there's also climate models which have shown the exact opposite. So these ones down here are showing that actually the variability in the El Nino system has actually reduced. And that's exactly the same we show on the Nino 4 index. Some models show an increase, some models show a decrease. So what does this mean? It basically is to demonstrate that actually the future is very uncertain. So we're not really able to capture how the El Nino system will change into the future with our current suite of climate models. So it's a really big unknown how it will change in the future. And it's really important for us to know this because it's going to have a really big impact on the ways that the coral reefs are going to be impacted by these marine heat waves. So we can look into the past, and I guess that's going to be kind of a different session as well. So we, rather than looking forwards into the future, we can look at fossil corals, or actually we can drill into living corals, and because they have kind of annual growth layers, we can look into the past, and we can make various measurements of those coral skeletons, of their chemistry and their isotopic composition, that tell us something about the conditions in which they grew. And we have in the past used these as basically, I guess, fossil weather recorders, allowing us to measure the intensities of these El Nino events in the past. So that's just a look forward to one of the future videos that we'll be looking at, see if there's evidence for El Nino change under past climates as well as into the future. Okay, so that's a lot there. We've been going for 40 minutes. So just to summarize the whole thing so far. So the Earth is getting warmer and the oceans are getting warmer because most of the heat increase of the planet has actually gone into the oceans. That's obviously causing sea level rise, which is not uniform over the whole globe. Different regions are experiencing sea level rise at different rates. And that has important implications for the medium to long-term viability of coral reefs in terms of their ability to keep up with sea level rise. That's kind of not even including kind of the other stresses that coral reefs are going to undergo, which will inhibit their ability to kind of keep up with rising sea level. One of those other stressors is ocean acidification. So by addition of carbon dioxide into the atmosphere, that's dissolving the ocean and it is acidifying it, which is reducing the capacity of organisms that secrete calcium carbonate to form those skeletons or shells. They're dissolving away. Also important is the oxygen content of the ocean, not particularly for coral reefs, because coral reefs tend to form near the surface of the ocean, where there's plenty of oxygen mixing from the atmosphere. But for other kind of ocean systems, ecosystems as well, the oxygen content is decreasing, and that's a major problem. And what we've been looking at in this video is these extreme warm events, these ocean heat waves. They are increasing in intensity, increasing in frequency, and they're increasing in duration over most of the globe, but there are some regions where that's not happening. And I guess lastly of all, the last point I made about we don't really know how the El Nino system will behave in the future. So there are lots of unknowns, which is, I guess, why you guys are becoming scientists to know the known unknowns. If that makes sense. Anyway, right. So feel free to watch that again, make some notes. It'll be fun, and we'll discuss this in the tutorial, particularly the future changes and heat extreme events and how we might deal with those. What technological solutions we might employ. Right, that's me done.